Picture this. You're standing in the middle of a machine shop.
Oh, yeah, with that very specific smell.
Right, the old oil, the coolant.
Hot metal.
Exactly. It's loud. You've got the hum of the motors, that rhythmic swoosh of the surface grinder going back and forth. And then just completely without warning, bang!
It is the sound that makes every single machinist's blood run cold.
Absolutely. It's this sickening crack that cuts right through your hearing protection. And we aren't talking about, someone dropping a heavy wrench or slamming a toolbox shut.
No, not at all.
We're talking about a high-speed projectile. In the world of CNC surface grinding, if you don't hold your workpiece down properly, that piece of metal doesn't just slip, it launches.
It effectively becomes a missile. And that is really the heart of what we're exploring in today's deep dive into the source material.
Yeah, it's a fascinating topic.
It sounds super technical, right? Like work holding for CNC surface grinders. But when you peel back the layers of the research here, it's actually this high-stakes battle against physics.
Yeah.
We're talking about friction, magnetism, heat.
And just the terrifying amount of kinetic energy stored in a spinning grinding wheel.
Precisely.
It's funny because I think most of us, when you picture machining, you assume the hard part is the cutting. Like the diamond wheel doing the physical work is the star of the show.
Sure, that's the intuitive thought.
But looking at the sources we've pulled for this deep dive, it seems like the unsung hero is actually the invisible force keeping the metal from moving in the first place.
In my experience, and looking at the documentation we have, when a shop is really struggling with quality control.
Like chatter marks.
Yeah, exactly. They get those ugly vibration ripples on a finished part, or they just can't hit their tolerances.
Yeah.
And they almost always blame the machine.
Oh, the bearings are shot, that kind of thing.
Right. The spindle is bad. But the research suggests that, honestly, 9 times out of 10, the machine is perfectly fine. It's the work holding. It's the grip.
The grip of gravity. Or, well, usually magnetism, as we're going to find out today.
Usually magnetism, yes.
So our mission today, for you listening, is to unpack the big contenders in this arena. We've got the heavyweights electromagnetic chucks, which seem to be the industry standard.
The undisputed king, really.
Right. Then we've got permanent magnetic chucks, which are a different beast entirely. We'll briefly touch on vacuum systems for specific materials. And then, of course, the old, reliable mechanical vices.
And it is not just about choosing one at random out of a catalog. It's about understanding why you choose one. Because if you get the math wrong here, you aren't just scrapping a $50 part.
You're destroying a $50,000 machine.
Or much worse, you could severely injure someone.
Yeah, the stakes are real. Okay, so let's start with the apparent king of the hill, the electromagnetic chuck. Based on the reading, this just seems to be the default setting for almost all surface grinding. Why is that?
Well, magnets are undoubtedly cool.
They are.
But in manufacturing, efficiency is the real currency. The electromagnetic chuck is the standard for a few reasons, but the absolute biggest one is access.
Access to the part.
Exactly. Think about a traditional clamp. If you use a mechanical clamp to hold a solid block of steel down on a table, where does that clamp have to go?
Well, usually on top of the block,
Right.
Or gripping the outer edges.
Right. And if you are trying to grind the top of that block perfectly smooth, a clamp on top is obviously right in the way of the grinding wheel.
Ah, I see.
You have to grind around it, stop the entire machine, unbolt the clamp, move it to a spot you've already ground, bolt it back down, and then try to finish the job.
That sounds incredibly tedious.
It's a nightmare. And it's a nightmare for precision because every time you move that clamp, you lose your reference plane. You introduce error.
Because you're shifting the part slightly.
Even by a microscopic amount, yes. But a magnetic chuck holds the part from the bottom.
Right, because it's sitting on the magnetic table.
Exactly.
Yeah.
That gives you what we call 5-sided access. You can grind the top face and all 4 side faces without ever unclamping or changing the setup.
That is a massive time saver.
It scales incredibly well, too.
Yeah.
Let's say you have to grind 20 small steel spacers at once.
Okay.
If you're using mechanical clamps, you are physically tightening bolts for every single one of those 20 parts. That takes time, and honestly, it kills your wrists.
Not to mention creating 20 different opportunities to, strip a bolt or get the tension slightly wrong on one of them.
Precisely. With an electromagnetic chuck, you just place all 20 parts on the table, you flip a switch on the controller, and zap.
Current flows.
The magnetic field engages, and all 20 are instantly locked in place, perfectly rigid.
It's basically like magic. You just turn on gravity.
It really feels like that.
But here's where it gets really interesting to me, looking at the physics of it. The sources talk a lot about the quality of the hold, specifically regarding flatness.
Yes.
I always thought a heavy clamp was the most secure way to hold something, like physically crushing it down into place. But the research suggests magnets are actually much better for precision work.
This is a very counterintuitive point for a lot of people getting into machining. When you use a mechanical clamp, you're applying what we call point pressure.
Because it's only pinching where the clamp touches.
Exactly. You're squeezing the metal at specific spots, usually the very edges. Now, steel seems really hard and stiff to us, but under thousands of pounds of clamping pressure, it behaves a bit like stiff rubber.
It flexes.
It does. If you clamp it too hard from the edges, you actually bow the part upwards in the middle.
Oh, I see where this is going. You clamp it, it bends a tiny bit in the middle, almost like a bridge arching up.
Right. It bows up just a few thousandths of an inch. Then you come across with your grinder and you make that bowed surface perfectly beautifully flat.
It looks perfect while it's clamped.
It looks flawless. But then what happens when you loosen the bolt and release the clamp?
The pressure is gone, so the metal just springs back to its natural state.
It springs back. And suddenly, that perfectly flat surface you just ground is now concave. It has a dip in the middle.
You've completely ruined the tolerance.
You have. A magnetic chuck doesn't squeeze from the sides. It pulls. And it pulls down evenly across the entire bottom surface of the workpiece.
It's a distributed force.
Exactly.
So it's hugging the part down rather than pinching it.
A firm, uniform hug. That is exactly how you achieve the tolerances we're seeing in the source material. We're talking about flatness in the range of 0.0001 to 0.001 inches.
That is mind-bogglingly flat. That's a fraction of a human hair.
It's incredible precision. But there's another layer to this science of flatness that I actually find even more fascinating, and that's heat.
Thermal expansion, right, because grinding is basically just rubbing a rock against a piece of metal really, really fast.
Yes, and that generates tremendous friction. Friction creates heat. Now, when metal gets hot, it naturally wants to expand.
Right.
Imagine you have that steel block mechanically locked in a vise. It gets hot, it wants to grow, but the steel jaws of the vise are immovable objects. The metal literally has nowhere to go.
So it has to bow up again?
It bows up right into the path of the grinding wheel. So you end up inadvertently cutting more material off the center than the edges.
Because the center expanded upwards into the cut.
Exactly. But with a magnetic chuck, the hold is incredibly strong downward, but it allows for microscopic lateral movement.
It lets it slide just a tiny bit.
Yes. As the part heats up, it can essentially breathe. It can expand sideways across the smooth table without bowing up into the wheel.
That is such a cool concept. The magnet is strong enough to keep it from flying off, but gentle enough to let the physics of heat do its thing.
It's a very delicate balance.
Yeah.
But we do have to make a major distinction here. We keep just saying magnet, but the source material makes a very big deal about the difference between the types of magnets.
Right, because getting this wrong can actually be really dangerous.
Extremely dangerous.
So let's unpack this. We have electromagnetic chucks, which we've been talking about mostly, and then permanent magnetic chucks. To the uninitiated, they both just look like heavy metal tables that things stick to. What is the actual difference?
The core difference is where the magnetic force is coming from. An electromagnetic chuck uses coils of copper wire inside. You run electricity through them, you get a powerful magnetic field.
And when you turn off the electricity, the field just collapses.
Instantly. Now, a permanent magnetic chuck has actual physical magnets built inside it, usually made of neodymium iron boron.
Those really powerful, rare earth magnets.
The exact ones. And because they are physical magnets, they are always on.
Wait, if they're permanent magnets and they're always projecting a field, how do you turn the table off to get the part off? Does the metal just stick there forever?
That's the really clever bit of engineering. You use a manual lever or a heavy wrench on the side of the chuck to physically slide the magnets around inside the housing.
Oh, you're physically moving them.
Yes, you are aligning or misaligning the magnetic fields.
Right.
When you pull the lever one way, the fields align, the magnetism reaches up through the surface and grabs your part. When you throw the lever the other way, you redirect that magnetic field to stay internal to the chuck. It basically short-circuits its own field, so the top surface releases the part.
Okay, so one uses active electricity, the other uses a physical lever. Why does that distinction matter so much in a shop?
It matters for two massive reasons: heat and safety. Let's look at the heat first. Remember we said electromagnetic chucks use big coils of wire?
Yeah, to run the current.
Well, running electrical current through wire creates resistance, and resistance creates heat. So an electromagnetic chuck actually gets warm just by being turned on, even before you start cutting.
Oh, I hadn't even said about that. So the chuck itself could warm up the workpiece.
Exactly. If you're chasing those millionths of an inch tolerances, the heat radiating from the chuck itself can transfer to the workpiece and warp it before the grinding wheel even touches it.
That's wild. But the permanent magnets?
Permanent magnets use zero electricity, so they run completely, 100% cold.
The cold advantage. That makes perfect sense for super high-precision aerospace or medical parts.
It does. And then there's the safety aspect, and this is the one that really keeps shop owners awake at night. What happens to an electromagnetic chuck if the power to the building goes out?
Well, it just stops being a magnet.
Instantly. If there's a heavy thunderstorm, or someone accidentally trips over a main power cord, and the power cuts, that electromagnetic chuck releases the part immediately.
But the grinding wheel is still spinning.
Right, because of inertia. So now you have a completely loose piece of steel sitting under a wheel spinning at thousands of RPM.
That is the projectile scenario we started the show with.
Yeah.
Permanent magnets, on the other hand, are completely fail-safe. The power can go out, the whole building's grid can collapse, but that magnet is not letting go of your part until a human being physically pulls that lever. That makes so much sense. So why doesn't everyone just use permanent magnets all the time? They sound safer, they don't heat up, they seem objectively better for precision.
They are fantastic, but they do have limits. For one, they're usually only practical for small or medium-sized parts. Making a massive permanent magnet table is incredibly heavy and expensive.
Plus you'd need superhuman strength to pull the lever.
Exactly. And secondly, they aren't easily automated. You need an operator to walk over and pull that lever. But an electromagnetic chuck can be tied into the CNC computer. And more importantly, it allows for what we call variable holding force.
Variable force. Okay, why would you ever want a weaker magnet? Don't you always want the absolute maximum grip so it doesn't fly away?
Not always. And this brings us to one of the most interesting phenomenons detailed in the source material. It's called the suck down.
The suck down. It sounds like a bad sci-fi movie title, but I have a feeling it's a major headache for machinists.
It is a classic trap for beginners. Let's say you need to grind a fairly thin plate of steel, but the plate is slightly warped from previous machining steps. It's got a bit of a bow in it.
Like a potato chip.
Perfect analogy. A very rigid steel potato chip.
Yeah.
Now you put that warped plate on a powerful electromagnetic chuck, and you turn the power to 100%. The magnet is so immensely strong, it literally sucks the bow right out of the steel. It pulls it perfectly flat against the table.
Which sounds, that sounds good, right? Doesn't that mean your problem is solved? The part is flat.
It sounds great. You come in with a grinder, you cut the top, and it looks perfectly mathematically flat, mirror finish. But then the job is done, and you turn the magnet off.
Oh. And the steel just springs right back to its original potato chip shape.
Exactly. The internal stress of the metal was still there the whole time. You haven't actually made the part flat. You've just forcefully held it flat while you cut it.
That's wild.
When you release the magnetic grip, that built-up warp comes right back, and now that beautiful surface you just ground is curved again.
So in that specific case, the magnet is actually too strong.
Right. And this is the beauty of the electromagnetic chuck. You can dial the power down on the controller. You use just enough magnetic force to hold the plate so it doesn't slide around, but not so much force that it sucks the warp out.
Oh, I see.
You grind it very gently in its warped state until one side is truly flat. Then you flip it over, crank the magnet all the way up to 100% because you now have a perfectly flat mating surface, and you aggressively finish the other side.
That's brilliant. You're using the adjustability of the tool to actually manage the internal stress of the material itself.
Exactly right.
But okay, what if you have a material that just isn't magnetic at all? We've been talking purely about steel and iron, but shops grind aluminum, copper, brass, plastics.
And that is exactly where the magnetic chuck hits its absolute hard limit. If the material isn't ferromagnetic, your expensive magnetic chuck is just a really heavy, really fancy table.
So what do you do? I think the sources briefly mentioned vacuum systems.
Yeah, vacuum chucks are great for certain things.
Yeah.
If you have flat, non-porous materials like big sheets of plastic or aluminum, a vacuum system can hold it down using negative air pressure.
But I'm guessing it doesn't have the brute strength for heavy grinding.
No, it doesn't have the shear strength. If you push too hard laterally, the part will just slide right off the suction. So for heavy work on non-magnetic stuff, we return to the humble vise.
The return of the mechanical vise.
Right. For brass, aluminum, or certain grades of stainless steel that aren't magnetic, you absolutely have to use mechanical clamping or heavy precision vices.
And the source material mentions something about complex shapes, too. Like, what if you're trying to grind something that's round?
That's another limitation of magnets. Magnets need surface area. They need a nice flat bottom to grip onto. If you put a solid steel sphere on a magnetic table, the actual contact point is tiny.
Just a microscopic dot.
Right. It won't hold safely at all.
Yeah.
You need a physical fixture to cradle it.
And what about angles? The source mentioned a specific tool called a sine vise, and that immediately brought me back to high school trigonometry.
Well, it is literally trigonometry in action on the shop floor. A standard magnetic chuck pulls straight down. But what if the blueprint says you need to grind a perfect 45-degree bevel on the edge of a part?
You obviously can't just balance it carefully on its corner.
No. A sine vise allows you to bolt the part in and then tilt the entire vise to a mathematically precise degree.
Using the sine formula.
Yes, using precisely machined metal blocks, called gauge blocks, to set the exact height of the tilt. And once it's set, it locks rigidly in place.
So it's really about providing rigidity against the cutting force, especially when the part isn't just a flat block.
Especially for tall parts. This is a huge safety point in the literature. If a piece of steel is tall and skinny, a magnet holding just the bottom footprint might not be enough to stop it from tipping over the moment the grinding wheel slams into the top edge.
Because of leverage?
Exactly. The grinding wheel, pushing horizontally on the top of the part, creates a lever arm. It can literally peel the part right off the magnetic table. For tall parts, you almost always need the physical lateral support of a vise jaw.
It really just boils down to a massive decision tree for the machinist. If it's steel and flat, use a magnet. If it's aluminum or an awkward shape, grab a vise. Super precise and heat sensitive, permanent magnet, big batch jobs, and automated electromagnet.
That is a perfect summary of the daily decision-making process.
Mm-hmm.
But I do want to circle back to the very beginning of our conversation, to that loud bang.
But projectile.
Right. Because we've talked a lot about efficiency and flatness and holding force, but the source material is very stark about the actual consequences of failure here.
Yeah, let's look at that chain reaction the expert in the article described. It's not just that the part flies off, hits the concrete floor, and you lose $20 of raw material.
Not at all. We need to visualize the sheer physics happening in that machine enclosure. A typical surface grinder wheel spins at several thousands of RPM. It carries a massive amount of kinetic energy.
Just a heavy stone spinning incredibly fast.
Yes. When a part comes loose, say the magnet wasn't strong enough or the part was too tall, the wheel grabs it. We call this climbing. The grinding wheel essentially tries to drive over the part, like a car tire spinning out in the mud, but at ultra-high speed.
And that just launches the piece of metal.
It launches the part with incredible tangential force. It truly becomes a bullet. But then, that part usually hits something immediately. It hits the safety guard, or what we call the stop iron.
A stop iron.
It's a heavy block of metal, bolted to the table, specifically placed there to catch loose parts before they exit the machine.
Okay, so it hits the stop iron, then what?
That sudden, violent impact shock loads the grinding wheel. And you have to remember, grinding wheels are made of bonded abrasive stone or ceramic. They are incredibly hard, but they are brittle.
Oh no, they don't bend.
They don't bend at all. They shatter.
So now you have the original metal projectile bouncing around, plus an exploding stone wheel.
It creates deadly shrapnel. Large chunks of abrasive stone flying everywhere at hundreds of miles an hour. It is basically a shotgun blast inside the machine enclosure.
And what happens to the machine itself in all this?
It's often completely destroyed. I have seen photos from these accidents where the main spindle, the thick steel shaft that holds the wheel, is visibly bent. Or the precision guide rails that the table smoothly glides on are deeply gouged by the flying steel part.
So a simple mistake can take a $100,000 piece of precision equipment and turn it into scrap metal in a fraction of a second.
All because you didn't check if the electromagnet was turned on, or because the part wasn't seated flat, or honestly just because you didn't wipe the table clean.
The source mentioned that explicitly. Ensure the contact surface is meticulously clean. But how much does a little bit of shock dirt really matter under a heavy block of steel?
It matters immensely. Magnetic force follows the inverse square law. It drops off exponentially with distance.
Meaning even a tiny gap kills the pull.
Exactly. If there is a single tiny metal chip from a previous job, or even just a piece of hard grit under your part, it lifts the steel up by just a few thousandths of an inch.
You're creating an air gap between the magnet and the part.
And that tiny air gap might reduce your total magnetic holding power by 50% or more.
Wow.
So a dirty table isn't just sloppy craftsmanship. It is actively dangerous.
It really emphasizes that work holding isn't just a passive thing. You don't just set it and forget it. It is an active, critical part of the safety protocol.
Absolutely. The machine's CNC controller doesn't know if the part is held securely. It has no idea. It will spin the wheel and run the program regardless. It is entirely up to the human operator to understand these unseen forces.
The heat, the magnetism, the friction.
Yes. And to choose the right tool to physically manage them.
So, if we boil all this down for you listening, whether you're prepping for a manufacturing meeting or you're just trying to understand how the things around you are actually made, it's not just about clamping things down tightly. It's really about managing energy.
That is the perfect way to put it. You are managing the cutting energy of the wheel, you're managing the thermal energy of the heat, and you're deploying the holding energy of the fixture to keep it all in balance.
Right. If you're grinding steel and you want speed and efficiency, you go electromagnetic. If you need that thermal stability and guaranteed safety during a power loss, you use a permanent magnet.
And for everything else, the aluminum, the plastics, the awkward angular shapes, you rely on the mechanical leverage of a vise.
And in every single one of those cases, you have to respect the physics. Because if you disrespect the physics will disrespect you. Loudly.
Loudly, the operative word there.
You know, this whole deep dive has really made me think about something broader. We trust these forces so implicitly in our daily lives. Well, think about the machinist with an electromagnetic chuck. They flip a switch, and this completely invisible force magnetism locks a heavy piece of steel in place.
Right.
You can't see the field. You can't touch the force itself. You just have to trust that it's there and that it's holding.
And as we learned, if the power grid hiccups, that trust is broken instantly.
Exactly. It makes you wonder what other invisible systems we rely on every single day without a second thought.
That's a great point.
We trust the invisible Wi-Fi signals to carry our critical data. We trust the hydraulic pressure in our brakes to engage when we press a pedal at 60 miles an hour. We trust the power grid to just stay on.
We really do live in a modern world, held together by invisible handshakes.
Right. And just like the skilled machinist who has to know exactly when to trust a permanent magnet versus an electromagnet, maybe we should all be a little more aware of which of our daily systems are truly fail-safe.
And which ones are just one switch flip away from letting go.
That is something to mull over the next time you hear a loud bang. Thanks for joining us on this deep dive into the source material. We will catch you on the next one.
Stay safe out there.